Okay, so NCEA Level 2 Electricity and Electromagnetism standard has three main topics, and these are static electricity, and then we have DC circuits, and finally we have electromagnetism. Okay, so, and in this video, we are just going to focus on the static electricity part of this standard, external standard. So let's start with static electricity. Okay, so it's called static electricity because, as you know, the word static means stationary or not moving. And over here, we are talking about charges that are staying on an object. So it's not flowing like in a circuit. There's no closed path for the charges to flow. So we are just focusing on one single object, which is either positively charged or negatively charged. And we know that when something loses electron, then it becomes positively charged. Or if it gains electron, it's always the electrons that are either lost or gained from an object, because object can have free electrons. Then if something gains electron, then it becomes negatively charged. Okay, so the first thing we want to understand is the relationship between the amount of charge on an object, and we are going to denote it with capital Q, and charge, its SI unit is coulombs, and symbol is capital C, and the number of fundamental charges, so how many electrons it has gained or lost, so number of charged particles. It could be electrons in some cases, or you might be spraying, for example, charged droplets on an object. So this is the number of charged particles we are talking about, and we use the symbol small n to denote that. And the relationship between these two and the charge on those particles. So charge on particles. I think it's better to say charge on each particle. And we are going to call this small q. This is also charged, so its unit is also coulombs, C. So the relationship between these three things is capital Q, the amount of charge on an object, is equals to the number of charged particles it has gained times the amount of charge on each of these particles. So this is one of the formulas you will get in your formula sheet. And we have to use this formula to basically maybe calculate the amount of charge, or calculate the amount of charge on each particle, or the number of charged particles it has gained. So let's look at an example. Let's say we have a metal plate over here, and this plate has gained some electrons. So it has now become negatively charged because of these excess electrons. And the number of electrons it has gained is, let's say, 1000. And we know the charge on each of these electrons it's a fixed number, it's a constant, and that's 1.6 times 10 to the power of negative 19 coulombs. So then the total amount of charge, and it's negative because electrons have negative charges. So the total amount of charge that this metal plate will gain is N times Q. So it's going to be 1000, because it has gained 1000 electrons, times the charge on each electron, 1.6 times 10 to the power of negative 19. And that, if you do the math using your calculator, you'll get a negative number because it's negatively charged, and times 10 to the power of negative 16 coulombs. So that's the amount of charge on this metal plate. Okay, so this was our first example. So let's say it's example 1. Now we can look at another example question. So let's say that's our second question using this formula, example 2. And now I have an object, and that object has an overall positive charge, and I know the amount of charge on this object is, let's say, 0.025 coulombs. So I know what's capital Q, and this object has become positively charged because it has lost electrons. So we know that each electron it has lost has this amount of charge in it. So that's our Q. I know it's negative, but we are not worrying about the negative sign because we know it has lost that electron. That's why it has become positively charged. And now we want to figure out how many electron it has to lose in order to gain this amount of positive charge. So we want to figure out what is our N, number of electrons being lost over here. So we are going to rearrange that formula. Q will start with the Q equals to NQ formula, and then we are going to rearrange it to solve for N, the number of charged particles, and that is equals to capital Q divided by small q. Because we have moved this small q to the other side, this has moved to the other side, so that's how we rearrange the equation. And then you can substitute the numbers in here. So you can put Q as 0.025, that's our capital Q, the total amount of charge on the object. And then the charge on each electron is this. Make sure you put a bracket around it if you're using your calculator, and then you can do the calculation. So if I do the calculation, let me use my calculator. So I'm dividing 0.025 and then divided by 1.6 times 10 to the power of negative 19. So close the bracket. So my answer is 1.56 times 10 to the power of 17. So that's how many electrons it has to lose in order to gain this amount of total charge. Okay, so that's your second example. And we can have a third example where, let's look at another example. And this time I am charging this sheet over here, and we are spraying some charged, let's say, droplets on this sheet over here. And because of that, this sheet has now become positively charged. Each of these droplets are positively charged, and it has now gained a total amount of positive charge of 0.056 coulombs. And I know the number of charged particles that have sprayed onto this sheet is 2000. So I know what my little n is. And using that, I have to figure out what's the charge on each of these droplets. So we'll start with our same formula, the relationship Q equals to capital Q is equals to N times small q. But this time we are trying to solve for small q, the charge on each of these droplets. And so we'll rearrange this equation and move the N to the other side. So it becomes small q is equals to capital Q divided by N. And let's substitute our numbers. 0.056 divided by 2000. So total amount of charge divided by charge on each particle. And if I do the calculation, 0.056 divided by 2000, I get 0.000028, or I can write it in scientific notation, which is 2.8 times 10 to the power of 1, 2, 3, 4, 5, 10 to the power of negative 5 coulombs. So that's the charge on each droplets over here. Okay, so that's everything from this part of the static electricity using the Q equals to NQ formula and then using it to solve for capital Q or N or small q. Okay, so if you want to practice more questions about using this formula Q equals to NQ, then you can answer the questions from your SciPad book, and the pages that you can work on is, I think, 237 and 238. So if you work on these pages, then there are more questions about using this Q equals to NQ relationship. Okay, so next what we are going to do is we are going to move on to the next topic from the static electricity part, which is electric field strength, sometimes also referred to as electric field, and electric field lines. Okay, so that's the next key topic from static electricity. So if you have charged particles or charged object, then it sets up an electric field around it. So let's say we have a positively charged particle and it's a spherical particle, and we can call it a point charge because it's not too big, it's small, and it has got positive charges around on it. Then what it will do is basically it will set up an electric field around it. So I'll show you the electric field with this color. So it's basically setting up an electric field around it. So this is just some area, some region around this positive charge, and I mean it extends all the way to infinity, but this is just a area, a region around this positively charged particle, where if you bring any other charged particle, then it will feel a force. So this area, this region around this positively charged particle, or it could be a negatively charged particle as well, any charged particle, the area, the region around it where any other particle will feel a force due to interaction between this charge and the other charge that you're bringing in this area is known as the electric field set up by this charged particle over here. So actually, if I bring in a positively charged test particle, so a positive test charge here, it's a positively charged particle, it's a test charge, and it has a charge of 1 coulomb, then it will feel a force away from this positively charged particle, because we know similar charges repel each other. And this force that this positive test charge of 1 coulomb will feel at that point is actually what it means by electric field strength. So electric field strength, basically electric field strength is denoted by the symbol capital E. I know it's similar to energy as well, but that's what we use for electric field strength. And it's measured in units of volts per meter or Newton per coulomb. Okay, so this electric field set up by a charged particle, it could be a positively charged particle or a negatively charged particle, is invisible. You can't really see it, but we can show it in a diagram through electric field lines. So we basically draw electric field lines around charged object to show the electric field strength in different areas around that charged particle. So if you have a positively charged particle, a spherical charged particle like this, like a point charge, then we can draw the electric field lines. We usually draw the electric field lines as, this is a positively charged particle over here. We draw the electric field lines pointing outwards away from this charged particle over here. So that's how the electric field around this positive charge is shown. Okay. On the other hand, if you have a negatively charged particle, then the electric field lines, which shows the electric field set up by this negative charge, is drawn as arrows pointing towards the charged particle, like this. And the density of these electric field lines, so how dense the lines are, is what shows you how strong the electric field is. So over here, if you can see, like close to the charged particle over here, the electric field lines are very closely spaced, so they are more dense. It shows the electric field strength is high over here. The E is large over here. But as you go further away from the charged particle, so for example, in this area over here, you can see the electric field lines are more spaced out. So it has a weaker electric field over there. It's not as strong as close to the charge. Same for the negative charge. Really close to the charged particle, the electric field lines are more dense. So E is quite strong. But if you go further away, the electric field lines are more spaced out, so less dense. So that means weaker electric field. So basically, the electric field strength is shown as the density of the electric field line. So therefore, it's proportional to the density of the electric field lines. So if you want to show really strong electric field, you have to draw more lines closely spaced. And if you want to show a weaker electric field, draw the lines more spread out, like how it's done over here for positive and negative charges. Okay? Charge particles, like point charge particles. And just remember that this electric field lines always, so the field lines always point away or outwards from positive charges, and the E field lines always point towards the negative charge. Okay, now in year 12, there is another setup that we commonly use for static electricity, and we have to understand the electric field for that setup, which is like parallel plates. So if you have not a single point charge, like a positive charge or a single negative charge, but instead you have two metal plates, and we have put positive charges on one of the plates by connecting it to the positive terminal of the battery, and negative charges, the same amount of negative charge on the other plate by connecting it to the negative terminal of the battery. Then it sets up an electric field in the area between the plates, and this electric field is drawn as lines pointing from the positive charge plate to the negative. Oh, sorry. Let me use a different color. Yeah. Okay. So let's do. And this is a uniform electric field. Uniform means it's same everywhere. The electric field strength is same everywhere. So we can draw it with electric field lines which are spaced out evenly in between the plates. And then on the edges where the plates end, some of the electric field lines will be slightly sticking outwards. So like this over here. And these are known as fringes. So in between the plates, uniform electric field. So that's why I draw the electric field lines evenly spaced out, same density everywhere. And then on the edges, there are some fringes, some field lines that are sticking out. So that's how you draw the electric field, uniform electric field between two parallel plates. And this uniform electric field strength is given by the formula E is equals to V over D. So this is another formula that you will have in your formula sheet. This gives us the electric field strength in the uniform electric field strength in the area, in the region between two parallel plates, okay? Where V is actually the voltage between the two plates measured in volts. So for example, if I connect a voltmeter across the two plates and I measure the voltage between the two plates, and if it's V, that's what this V is. And D is the distance between the plates. Okay, so if you have the two plates, D distance apart from each other, then that's this D over here. And it has to be in meters. When you are using this formula to calculate anything, let's say electric field strength, then make sure that D is in meters. So this is your second formula. Okay? And then we can use this formula to calculate different things. So let's look at some examples. So let's say our first example is where we have two plates and the voltage across of the voltage difference between the two plates is 10 volts. So we have connected it to a battery so that the battery is providing 10 volts. That's the voltage between the two plates. And the two plates are, let's say, 10 centimeter apart. Okay? And then we have to work out what is the electric field strength, the uniform electric field strength between the plates. So we'll start with the formula. E is equals to V over D. E is 10 volts, which is fine, but D is in centimeters, so make sure you change it to meters. So divided by 100, that is 0.1 meters. And then if you do the calculation, it's 100 volts per meter. So that's the electric field strength between the two plates over here. So that's our first example. Okay, now we can use that same formula to calculate other quantities. For example, let's say we are given the electric field strength between the two plates is 20 volts per meter. So now we know the electric field strength and we know the two plates are 1 meter apart. Okay? And we have to work out what's the voltage difference between the two plates. So then we'll start with that same formula that you will get in your formula sheet, uniform electric field strength between parallel plates equals to V over D. But we are going to rearrange this formula. So move this D to the other side. So we get E times D is equals to V. Okay, so that gives us the voltage is the electric field strength 20 times the distance 1 meter. So it's just 20 volts. Okay, so that's the electric field strength. Sorry, that's the voltage between the two plates. So that's our second example. And we can look at a third example where we'll calculate, let's say, the distance between the plates. And we know the electric field strength. It's, let's say, 40 volts per meter. And we also know the voltage we have across the two plates, the voltage difference is 20 volts. And we have to work out how far away the plates are. So what's D? So again, start from the formula E equals to V over D. We have to first rearrange it because D is in the denominator now. So we have to first move it to the other side and it becomes E times D is equals to V. And then to solve for D, we will move the E to the other side. So then it becomes D is equals to V over E. Please do the rearranging of the formula properly, otherwise you will get the wrong answer. So let's now substitute the values. We have 20 volts and the electric field strength is 40. So that gives us half or 0.5 meters. So the distance between the two plates are 0.5 meters. So that's how you can use this formula to calculate different things, the uniform electric field strength between the plates, E, or the voltage across the plates, V, or the distance between the two plates, D. Okay, so if you want to practice more questions about drawing the electric field lines between parallel plates, or if you want to use the formula E equals to V over D to calculate different things, then you can answer the questions from these pages of your SciPad book, page 239 to 242, where you have more questions about this topic. So the next thing that we have to learn from this topic is force on a charged particle. So the next topic is the electrostatic force acting on a charged particle. So let's now try to understand that. So what we will have is the same setting with two metal plates, parallel plates, and one with positive charges on it, and the other one with negative charges, same amount of negative charges on it. And then we will have the uniform electric field set up between the plates, shown by this electric field lines, which are uniformly spaced, pointing from the positive charge to the negative charge. And then maybe on the edges, we have some fringes where the electric field lines are sticking out a bit. And now if we place a charge particle in this uniform electric field. So let's say I place a positively charged particle with charge Q on this uniform electric field. Then because of the charges on the left-hand side plate, which is positive, there will be a repulsive force pushing it to the right, because we know similar charges repel each other. And the negative charges on the right-hand side plate will attract this positive charge, because opposite charges attract each other. And as a combination of these two, repulsion and attraction, there will be a net force of F acting to the right. Okay, so this is the electrostatic force, which is acting on this charged particle Q placed in this uniform electric field because of the interaction between the positive charges and the negative charges on the plates and the positive charge of the particle. So you can calculate this force, this electrostatic force acting on this positively charged particle. So this is the electrostatic force acting on this charged particle over here, F, and it could be calculated as Q times E. So it depends on how much charge we have, the amount of charge on this particle placed in here, and it depends on the electric field strength set up between the two plates. So basically this E over here is the electric field strength measured in volts per meter, and this Q here is the charge on the particle, and it has to be in coulombs. Okay, so if I know these two things, I can work out how much electrostatic force will be acting on this charged particle. So this is the next formula that you will have in your formula sheet, and because this F is the electrostatic force, it will be definitely measured in units of newtons. Okay, so now in your exam, you can get questions where you might have to draw the labeled arrow to show this electrostatic force acting on a charged particle. So let's look at some question like this. So that's our first example question, example 1, where we have to draw the electrostatic force acting on negatively charged particles. So I'm going to take a negatively charged particle placed in this electric field over here. And we have to draw a labeled arrow. So we'll place the negatively charged particle in this electric field. So this is our negatively charged particle in the electric field. So now the negative charges on the plates on the right hand side will basically repel this negative charge. So there will be a force to the left because of that repulsion, and the positive charges on the left hand side plate will attract this negative charge. So combined there will be a net force to the left. So positive charge attracting this negative charge and the negative charges on this other plate repelling this charge. So overall there will be a net force acting to the left. So that's why we have drawn an arrow, labeled it with F to show that it's a force we are talking about over here, or we are showing through this arrow, using this arrow. And I think it would be a good idea to also just mention that it's the electrostatic force acting on the charged particle. So that's our first example over here, drawing the electrostatic force acting on the charged particle. Now you can get questions where you might have to calculate that force, or you might have to use that formula F equals to QE to calculate the charge or calculate the electric field strength. So I'll take a simple example where I know the electric field strength set up by the charges on the plates is, let's say, 20 volts per meter. You can even work out this electric field if you are given the voltage across the plates and the distance between the plates using the E equals to V over D formula. And then I know that, let's say I have a charged particle placed in that electric field, which is an electron. So I know its charge is negative 1.6 times 10 to the power of minus 19 coulombs. And I will have to work out how much is the electrostatic force acting on this electron placed in this electric field. So I'll start with the formula F equals to QE. I know Q is 1.6 times 10 to the power of negative 19. When you are working out the force, you don't have to worry about the negative sign on the charge. All you need is the magnitude, how much is the charge, not the sign of the charge. And then I will times it by the electric field strength, which is 20. So then I'll get roughly 3.2 times 10 to the power of negative 18 newtons. So that's the force, electrostatic force acting on this electron placed in this electric field, uniform electric field. Okay, so that could be your second example. Okay, and then let's say, for example, 3, we might have to describe what will happen to this electrostatic force as the charged particle is moving through the electric field. So if I let this negatively charged electron move in this electric field, what will happen is basically it will start moving to the left. So a little bit later, maybe the charged particle will be, this electron will have moved over here because there's a force pushing it that way. So it will start accelerating in that direction and it will change its position. It will move through the electric field. And the question is, you have to describe what will happen to the force that is acting on this charged particle. Will it change because now it's closer to the positively charged plate, or will it stay the same? So when you're answering questions like this, so basically we're describing what happens to F, the electrostatic force, as the charged particle moves in this E field, the electric field. Okay. So when you're answering questions like this, try to use the formula to justify your answer. So for example, we know that the force on the charged particle is Q times E. We have to explain what happens to this force as the charged particle is moving through the electric field. So we have to check what happens to Q and what happens to E as the particle is changing position. So we know that if the particle starts from, let's say, over here and then moves to a different location, because it's moving in that same electric field, E is uniform everywhere. So E over here is uniform. It's not changing. So it's same everywhere. Okay. And then Q is the charge on the particle. If it's the same particle, Q also is constant. It does not change. Okay. So both E is same everywhere and Q is same everywhere, no matter where the particle is, which means that neither Q nor E in this force formula is changing. So what will happen is F will stay the same. So it doesn't matter where the particle is in that electric field. As it's moving through the electric field, it's the force that is acting on it will stay the same. Now you might wonder, why is that? It's coming close to the positively charged plate and it's moving away from the negatively charged plate. So now it should have bigger force because maybe the positive plate will attract it more because it's close to it. But this force, remember, this is a combination of the two electrostatic forces, both from the positively charged plate and the negatively charged plate. So you're right that it's moving closer to the positively charged plate, but it's now further away from the negatively charged plate. So the combined effect of these two forces is that the net force does not change, it stays the same. So that's a common question in your exam as well. What happens to the force as the particle moves through the electric field? Nothing happens, it stays the same. Why? When you're explaining, start with the formula, say that the force depends on the electrostatic force depends on the charge on the particle, which is staying the same as it moves through. And it depends on the electric field strength, which is uniform, which is same everywhere in that area. So that's why F will also remain the same. Okay. All right. So I think that's all from force on a charged particle. And again, if you want to practice more questions about this force from your book, then you can work through some of the pages on your SciPad book, which is page 243 and 244 up to 246. So we can work on SciPad pages 243 to 246. Okay. Okay, so the last part of this static electricity topic that we have to learn is actually electrostatic potential energy. So the last thing we are going to revise is electrostatic potential energy of a charged particle in an electric field. So what we are going to look at is the same situation where you have two parallel plates and then you have positive charges on one of the plates and then you have got negative charges on the other plate, and there will be uniform electric field set up in the region between the plates, shown by these evenly spaced out lines. And then if you place a charged particle in this electric field, so let's say I'm going to place a positively charged particle here, it could be a negatively charged particle as well. Then because of the interaction between the electric field set up by the charges on the plates and this charged particle, we have seen that there will be a net force of F acting on the particle to the right in this situation, and this electrostatic force will do the work. So if you let the particle move on its own, this electrostatic force caused by the electric field will push the particle forward and it will accelerate the particle in that direction. So if the particle moves from this point all the way to here and it travels a distance d, so the force will do some work moving it in this direction, and the amount of work done will be equals to the change in the electrostatic potential energy. So over here, because the electric field is doing all the work, so we will basically have a change in electrostatic potential energy, and you can calculate how much electrostatic potential energy it has. Over here, it will be losing electrostatic potential energy because the force is doing the work. So all of that work is equals to the amount of electrostatic potential energy lost, and that energy can be calculated as the work done by the force, which is force times distance. And we have seen earlier that this force, electrostatic force, can be calculated as Q times E. So then the change in electrostatic potential energy over here is Q times E, that's the force on the particle, times the distance the particle has traveled. This is how you can calculate the change in electrostatic potential energy, and this is another formula that you will get in your formula sheet that you will have to use to do lots of calculations in static electricity. Now over here, this we have seen that this left part over here, this one is the change in the electrostatic potential energy. It could be gained or lost. In this specific situation, we are losing it because the electric field is applying the force and doing the work, moving the particle over a distance d. On the other side, Q of the formula, Q is the charge on the particle over here, and it has to be in coulombs. E is the electric field strength. So it's the electric field strength set up by the charges on the plate, and that's in volts per meter or newtons per coulomb. And this D, be careful about this D over here. D is the distance traveled by the particle. So this is the distance traveled by the particle. It's not the distance between the plates. If the particle travels from one plate to another, then it could be the same distance, but it could travel from some other point, starting from some other point to some other point as well. So D can be different from the distance between the plates, okay? And it has to be in meters. So using this, we can calculate how much electrostatic potential energy the particle has lost or gained. And then we can use conservation of energy, because we know whenever energy is gained or lost, it has to be coming from something else. So conservation of energy tells us that if we are losing a form of energy, then it has to be transformed into some other form. Over here, because we are losing electrostatic potential energy, that's the lost form of energy, then it has to be equals to some other form of energy over here, which is kinetic energy, because the particle will gain speed, it will start traveling, it will accelerate because of the force, and then it will start moving faster and faster. So it's gaining kinetic energy, and these two energies must be equal due to conservation of energy. And from that, you can do lots of calculation. So if I say the amount of electrostatic potential energy lost is this, and that will be equals to half mv square, the kinetic energy gained. And then from this, you can rearrange the equation and solve for the speed. So if I move the 2 to the other side, it will be 2qEd, and then I have to move the mass to the other side as well. That will be divided by m, and then to get rid of the square, we have to do square root. So this is how you can calculate the speed of the charged particle after it has moved through a distance d. It could be opposite as well. So you can have a charged particle, let's say a positively charged particle over here. In that case, the electrostatic force will be pushing it this way. And let's say you want to move the particle from here all the way to here, close to the positively charged plate. In that case, you have to do the work pushing the particle against this electrostatic force. So in that case, the work is done on the particle. It will gain electrostatic potential energy. So if the particle was already traveling at a speed v over here, and it had some kinetic energy to start with, then as the particle moves through this electric field, it will have to use its kinetic energy, and that will get transformed into electrostatic potential energy. So that's how you can use conservation of energy, electrostatic potential energy changing into kinetic, or the other way around, to do lots of calculation about the speed and the force and the distance of a charged particle moving through an electric field. So this is the last part of this topic. And if you want to practice questions about this electrostatic potential energy and conservation of energy, I would recommend you check the following SciPad pages. So I think the SciPad pages that we are talking about over here starts from 247. So 247, and I think it goes all the way up to 250. So you can do questions from these pages. And that's all the key ideas from static electricity. And now I would recommend that you look at some past exam questions. Every year there's at least one full question about static electricity, and then try to work through those questions, past exam questions.